Turned on. There we go. All right. So you guys can see, as I kept saying in class, right? There's the revised test announcement there, um, for a week from Wednesday, right? Okay. And so don't forget that the sample test is posted right on the Blackboard page right there, and I will post the answers there probably Wednesday. But I wanted to give you a chance to look at the sample test first, the blank sample test first, before you looked at the answers. So even after I posted the answers, you should work on the sample test. That's important, but you should try to work on it without having the answers in front of you, right? Okay, so try to do it independently and then check your answer. Don't be, looking at the problem and looking at the answer simultaneously, because that's not really going to help prepare you for the that's not going to help prepare you for the test. Now, also remember, you can bring, of course, a calculator with you. That's fine. That can help you do computations. That's not going to help you with any of the the math on this test, other than just arithmetic. And then you can bring a standard size index card to the test. Standard size index card, right? So any standard size index card, and you can write on there anything that you want. So if there are formulas that you want to recall, or even problem examples if you want to, um, you can write that on the index card. So anything you fit on the index card, you can write on there. That's fine. So that's what you can bring to the test. Of course, what you write with, right? Okay. So in addition to looking at the sample test, also be thinking about what you're going to put on the index card. Like for instance, I don't know, the formula for projection, right? Okay, that would be one that you might forget. I don't think or the formula for the angle between the cosine of the angle between two vectors, right? Or the formula for the direction, each of the direction angles, right, in 3 dimensions. uh that's just off the top of my head, and we've got other things coming. So you can continue filling things out onto that index card. I think dot product is pretty easy though, so I don't really think you need to write down the formula for dot product. Okay. Um, all right. So anyway, so that's the test, right? And you've got a homework that's due tonight. So on the dot product, and so we spent quite a bit of time with that. And then we're going to talk today about cross product, which is another one of these operations for vectors, which doesn't have um, a scalar analog. Okay, so this is an operation that's special to vectors, unique to vectors. Like the dot product also is unique to vectors. But what's different for the cross product is when you take the dot product of two vectors, you get a scalar, you get a number. But when we take the cross product of two vectors, we get another vector. Okay, so the cross product of vectors results in a third vector. All right, and it's a little bit harder to carry out that computation. But once you've done a couple of examples, it's pretty easy. All right. Okay, so there's our homework list. That's all the homework that we'll have before the test. Okay. So notice that homework is due at the time of the test. Oh, it's due at the time of the test on Wednesday. Okay. Because you need to have done this one before you come to take the test, right? So of course these are due at the usual midnight hour. Okay. All right. So much for that. I know we have some questions. So Elijah has a question, but if other people have questions on dot products, then it's on dot products, right? Then let me know. Okay. Is it the last one? Uh, yes, it's the rest of number, but rest of number 10. Oh, was that the angle between two curves? I thought we finished that. We done. This is for later. Yeah. Did it for did it for there were 2 points where they intersected, right? They intersected at the origin. Yeah. Oh, how to, yeah. Okay. So, I think, let me see if I can find, I got to find where we were writing at though. Let me see if I can find that. Because we were writing on that problem, right? Somewhere in the notes. Oh, is this it? Oh, there's the picture, right? Okay. And so you were, so we went through this pretty completely and ended up with 45 degrees right there. I see theta is 45 degrees. The angle between the two curves here at this intersection point. That's because there are the two tangent lines. So what we were really finding, remember, was the angle between the two tangent lines, correct? Okay. And we did that by finding vectors corresponding to the tangent lines and then finding the angle between the two vectors, right? And so we have a formula for the angle between two vectors, right? Did I write that? Did I repeat that? Yeah, there it is. All right. There's the formula for the cosine of the angle between two vectors, right? And then you can apply arc cosine to get the angle itself, correct? All right. So, but yeah, this one is confusing, and I just sort of I just sort of treated it rather quickly because it's kind of a special case. All right. But you were trying to go through the mathematics and got it got messed up there. I don't. You really cannot go through the mathematics completely, Elijah. That's so not surprising that you were trying to do that. You got foiled. It's not so bad for the parabola here, y equals x squared. So what we're trying to do there is find the tangent line to the curve here at 0, 0 for this parabola, which is y equals x squared. So you find the derivative, right? And then you evaluate the derivative at the origin, that intersection point. And that value, of course, suggests what the slope of the tangent line is at that point, correct? And then you use that to construct a vector, right? So you use the slope to construct a vector. That's what we did. And then you do the same thing for the second curve, which in this case is x to the 1/3 power, which is cube root of x. So you do the same process for the cube root of x and to generate a vector that corresponds to the slope of the tangent line at the origin. But the problem is the tangent line there at the origin is vertical. Okay, so that's probably what I'm guessing. That's what messed you up. All right, so yeah, that's right. So you got 0 as the slope here, all right, which means this tangent line is flat. So what would be so it's horizontal, right? So what would be a vector that you could use as corresponding to the slope? What's the easiest vector you can think of there? Ah, yeah, that's right. Okay. So you would use I guess if we want to I guess if we want to use the notation there, the same variable names that are in the formula, we could call ui. All right, that's the vector that matches the tangent line here, right? Okay, and any horizontal vector will do. So actually, any multiple of I would be okay, but why not just use one I, right? Okay, any vector that's just a multiple of I and doesn't have a j component will be a horizontal vector. All right, so so I think the easiest one to use there is just u equals I. Okay, all right, and then same thing, right? You want a vector that matches this tangent line, the slope of the tangent line for x to the 1/3 power. But did we? Where's our derivative of x to the 1/3 power? We have it here, right? Is this it? Yeah, right there is the I don't know if y'all can see me pointing to it. Right there is the derivative of x to the 1/3 power. And so if you try to evaluate that at 0, Elijah, what goes off is what? Well, you plug 0 in for x, and of course you get undefined, right? Okay. Well, when you have an undefined when you have an undefined tangent line, well, there's several things that can go wrong that can cause you to have an undefined tangent line. So you really do need to see a picture of the curve to understand what's happening. You can get undefined tangent lines in various ways, like if your curve, let me lay this down. All right. So if you just to elaborate on that point, if you're that comes up frequently, sometimes in this course. Well, sometimes it comes up. If your curve looked like this, also the tangent line would be undefined at the origin, okay? Because you have a sharp turning point there. You don't have tangent lines at sharp turning points, okay? And so that would cause the tangent line to be undefined. But another thing that causes the tangent line to be undefined is if the I'm sorry, that causes the tangent line is not undefined, but the slope of the tangent line is undefined. So another thing that causes the slope of the tangent line to be undefined is if your tangent line is vertical like this. So you really need to see the graph of x to the 1/3 power and say, oh, I see what's going on here now. The tangent line is vertical. That's the problem. That's why I come up with an undefined derivative, okay? An undefined slope for the tangent line. Well, okay, great. If the tangent line is vertical, then I just have to find a vector that corresponds to a vertical line, and I can use what? J, sure, right. So we can call here V the second vector in, this formula I'm getting ready to apply, right? We can call that J. Does it work now if we do this, or does something go wrong? So we have the cosine of theta there is the dot product of I times J. What's the dot product of I times J? Yeah. So if you take I times J, see, here's I is 1, 0, right? And J is 0, 1. Yeah, it would just be 0, right? Okay. You would just get 0. So it doesn't matter what the denominator is, right? It doesn't matter what the denominator is. Actually, it's 1, isn't it? Because you have the magnitude of U times the magnitude of V, but we said U was I and V is J, and they both have magnitude 1. So you would get 0 divided by 1 here, which is 0. Okay, so the cosine of theta is 0, which means theta is what? What angle has, what's the first angle that has cosine 0? Pi over 2, right? Yeah. So theta there is 90 degrees. There's your answer. Okay. Yeah. Right. Yeah. Okay. So what was throwing you off, the undefined slope?
Yes, actually, I steps said back. So
Oh, oh, I see. Okay. So remember when two vectors are perpendicular, isn't it right? Perpendicular, their dot product is going to be 0, right? So whenever you get a dot product of 0, remember that means the vectors are perpendicular. Keep that in mind, okay? Because that's an important and useful fact. All right, okay. The dot product is 0 when vectors are perpendicular. Is that shown somewhere here as a rule somewhere in the notes about dot products? Oh no, this isn't the dot product note. I'm sorry, but this is the note after that. Yeah. Yeah. Right. Right. Okay. Because remember the and that's easy to remind yourself why that's true, right? Because of this formula, correct? Okay. The angle between the two, the cosine of the angle between the two vectors, right, is given by that formula, right? So if the angle is 90 degrees, right, if they're perpendicular, then this fraction has to turn out to be 0. But the only way this fraction can be 0 is if the top is 0, right? So that means the dot product has to be 0. Dot product has to be 0, right? So That's a test, right, for perpendicular vectors. If you take their dot product and get 0, then you know they're perpendicular. Okay. Okay. We're going to see a similar test, I think, today for parallel vectors. All we really know about parallel vectors so far is they have to be scalar multiples of one another. So for two vectors to be parallel, one of them has to be a multiple of the other. Okay, but I think today we're going to learn a shortcut for, well, you may not think of it as a shortcut. It's pretty easy to see when one vector is a multiple of another, but we're going to learn another test for parallel vectors today. Okay. All right. Is that it? Not the truck problem? I really don't want to go through the whole truck problem, so it'd be beneficial if we didn't. Is that on this one? Yeah, so that's going to be a projection just like the example that we did in class yesterday with the boat, except just translate it to that truck. Okay, so just try to go through all those steps with the truck. All right, I'm going to move on then. So if you, I hope. Well, I need to ask. Okay, I'm not trying to rush you. Do you have other questions? Okay, let's talk then about cross products. So this is actually kind of fun, and the cross products are very useful. All right, so again, this is just an operation with vectors, and so here is the notation that we use for cross product. So you can see where the term cross product comes from, because we're going to use that cross there, right? That little tilted cross there, right? That's grade school multiplication, right? So we're going to use the grade school multiplication symbol also for vector cross product. But now when you take the cross product of two vectors, you get a third vector. So notice your cross product vector has three components. You know, it's got the I component, the J component, and the K component, right? And then you just have to figure out what the coefficients of the I, J, and K are in the cross product. And notice you have kind of what look like ugly formulas to remember. They're not complicated, but ugly formulas to remember to get these coefficients. Don't try to remember this formula, all right? Because I'm going to show you how to do this easily so that you'll be able to reproduce the formula, all right, for the coefficients in the cross product. The only thing you want to remember here is cross product of two vectors is a vector, all right? So it's not a scalar. It's going to be another vector. All right, so let's try this here. And I'll do one, and then I'll let you do one. And so try to watch carefully now what I'm doing, okay, to simplify this process. All right, so we're going to take the cross product of I minus 2j plus k, that vector. It's kind of helpful to have the vectors written in that standard form of ij and k, right, as combinations of ij and k. But it doesn't have to be. It can be written in component form too. And v here is 3i plus j minus 2k. All right. So to calculate the cross product, here's the system that I'm going to use. All right. We're going to write the two vectors kind of as a matrix. So in a square matrix, actually. So it's going to have 3 rows and 3 columns. If you don't know what the word matrix means, that's fine. I'm just going to write a square here, a table here with 3 rows and 3 columns. So the first column is going to be I, J, and K. All right, so that's always fixed. And then in the second row, write the coefficients of the first vector. The coefficients of the first vector in the product. Make sure you write the first vector first, because cross product is not commutative. All right. What I mean is I cross V is not going to turn out to be the same as V cross, U cross V is not going to turn out to be the same as V cross U. All right. They're slightly different. So, so make sure that you write your vectors in the proper order in this table that I'm creating. So let's see, what are the coefficients of U here? It's 1, -2, and 1, right? So that's what goes into the second column. And then the coefficients of B are 3, 1, and -2. Of course, make sure you get the coefficients of the I, J, and K in the proper column, right? The I coefficients go in the first column, the J coefficients go in the second column, and the K coefficients go in the third column. All right, now here's what we're going to do. We're actually going to compute what is mathematically known as a determinant, but you do not need to you don't need to remember the phrase determinant. That's actually what I'm computing here, but you don't have to remember that phrase. Here's the process. All right, mentally, or if you want to do it physically, you can think of blocking out the first column. Okay, so block out that first column in your mind. Remove the first column. All right, so that leaves you with the second two columns. All right, now with those second two columns, we're going to compute a cross product. Here's the cross product. I'm going to take this diagonal, multiply those two, and then this diagonal, multiply those two, and I'm going to subtract. So you're going to take this diagonal product minus this diagonal product. All right. Easy, right? So remember, you blocked out the first column. You're just working with the second two columns. Take this minus this, that cross product. Let's see, what is that? So -2 times 2 is, oh, this is a -2. So -2 times -2 is +4 minus 1. Did I do that right? Let me write that down. So +4 minus 1. Remember, you take this product minus this product. Okay, so you get 4 minus 1. And then that becomes the coefficient of I in your cross product vector. Just that easy. Now, you're going to repeat this process. But next, you're going to block out the second column. So mentally there, or if you want to, you can do it. Just scratch it out on your paper. Okay, block out the second column. And you perform the cross product again. So we get what? See, this column is gone. So you take 1 times 2 minus 1 times 3. Let's see, 1 times 2 is 2, right? Minus 3. Is this -2? Did I erase the minus? Yeah, okay. Thank God y'all stopped me there. All right, so this is -2, but still -3, right? So that's a -2 minus 3. All right. Now, however, that is going to become the coefficient of the J, but you must change the sign. So here, put a minus. So you don't do that on the first one. You do it on the second. You're not going to do it on the third either. So on the third coefficient, you'll be back to plus. You alternate signs. So this is positive. That's fine. Then subtract this one and now add the next one. Well, what's the next one going to be? Block out the K column then and do the cross product again. So you get 1 times 1 minus 3 times a -2. So what is that? 1 times 1 minus 3 times -2 is -6, right? But you're subtracting, so that's going to be +6, right? 1 times 1 minus 3 times -2. So it's really 1 plus 6, right? And that becomes the coefficient of decay. That's it. So there's your cross product. That wasn't that bad, was it? 3i minus -1j, right? So that's plus j and then plus 7k. Did I make an arithmetic mistake? Oh, that's -2 minus 3, right? Okay, yeah. So this is +5. Yeah, all right. So this is so this is exactly where you're going to go wrong with cross products. there's a little bit of arithmetic, right? And there's a lot of subtraction. So it's easy to mess up the arithmetic because when you're subtracting minuses, right? So that's where things can go astray when you're doing cross products. Um, let's do a really quick check to see if this is correct. Okay. So I'm going to give you a secret here. It turns out that the cross product of two vectors is perpendicular to both of the vectors, right? So if you, for some reason, want to find a vector that's perpendicular to both u and v, you just take their cross product, okay? That sounds like that's not just kind of piece of trivia actually, but it turns out that we'll want to in the very near future find vectors that are perpendicular to two given vectors, and this is how you do it by computing the cross product. Now, how can I check? So there's my cross product. Let's call that let's give that a name. Let's call that W. All right. Let's pick another letter there. So how can I check to see if W is indeed perpendicular to one of those two vectors? It should be perpendicular to both, but I'm just going to check one. Yeah, you do the dot product, right? What we just talking about. So is this true? Does this turn out to be 0? God, I hope so. Okay, let's see. So let's do that dot product. How do you do the dot product there? Just multiply coefficients, right? Okay. So let's see. This is 1 times 3, right? Is 3. And then minus 2 times 5 is minus 10. And then is this 1 times 7 is 7? Is that 0? Yeah, so we have a chance that we got the right cross product because it is indeed our cross product is indeed perpendicular to u, but it should also be perpendicular to v. Okay. All right. Okay, look now. There's no sense in watching me do this. Okay, so I'm gonna let you try one, and we're just gonna do it in reverse because remember I promised you that these two things are not the same. All right, u cross v is not the same as v cross u. So cross products are not commutative. Cross product not commutative. Dot product is commutative. You can reverse the order in which you're taking a dot product, but you can't do that for cross product. So I want you to try now. U cross v. Wait, I can't. Maybe you can't even see them. Let me write it up here. So that's what I want you to try to do there is as opposed to u cross v, try to v cross u with the same two vectors. All right. So try to arrange them and then do those 3 cross products that are involved in finding the cross product and to get the coefficient. See if you can do that. See what the difference. It really only takes like 2 times, I think. That's my it only takes doing this twice, I think. So Okay, did I get some coefficients there? So let's put down our candidate there. So what's the I component there? That of that cross product. What times I? Minus 3 times I. And then what about for J? Minus 5 times J. And then for K, minus 7. Oh, so oh, that's right. Did y'all get that? Did I get that right? I'll do that. Oh, great. Okay. So, so notice there. Notice that the cross product V cross U is just the negative of the cross product of U cross V, right? Okay. So they are related to each other, but they're not the same. So there's another rule to remember. V cross U is the negative of U cross let's see what happens with V cross V. Okay, what do we do when we cross a vector with itself? So probably something not good happens, right? So let's write down what were the coefficients for V. Can y'all remind me of those? What now? 3, 1, -2. And so let's write this down twice, and then let's compute that cross product, right? So again, ignoring the first row, right? I'm going to get 1 times a minus 2, which is -2, right? And then minus -2 again, 1 times a minus 2, right? Okay. And so that would be minus 2 plus 2, right? Times I. And then ignore the middle column, right? So 3 times a minus 2 minus 3 times a minus 2 again. So that looks like minus 6 plus 6, right? Times J, but don't forget you're going to change that middle sign to negative. And then for the K, let's see, we can add that one on. But so wipe out the third column and do this cross product. So you have 3 times 1 minus 3 times 1 again. So that looks like 3 minus 3, right, times K. And voila, see nothing. We knew something strange had to happen there, right? And so indeed we get 0, right? Okay. You get the 0 vector out of this. All right. So anytime you take the cross product of a vector with itself, just get 0 vector. Now, of course, we can mix up cross products and, oh, I thought I had another example, but I don't. Okay. All right. Well, we can mix up cross products and dot products, right? And we can mix up cross products with scalar multiples as well. So here are some of the algebraic properties of cross products. And these are not really crucial to memorize these because I don't really think they are things that we have to recall in particular in many instances. But just remember, cross product does not have the same properties as scalar product or dot product. Okay. So we already mentioned, right? Cross products are not commutative. You cannot reverse the order of cross products and get the same result. And here's one that we already had experimented with also, right? A vector across itself is going to be 0. So, and whenever you're required to do that, take the cross product of a vector with itself, just remember, oh, that's going to automatically be 0. So you don't have to go through all that. You don't have to go through all that multiplication. And then you can combine cross products with dot products, right? And this particular combination where we take a cross product of two vectors and then take that vector and use that as a part of a dot product with a third vector. This is called a triple scalar product. No, I'm saying, I think I'm saying that triple scalar. Oh yeah, this is triple scalar product. So when you combine cross products with dot products, can do that, and that sort of operation is called a triple scalar product. Now, what's more interesting to us are going to be the geometric properties of cross products, okay? And so these are really going to be helpful to us. In particular, the first three, okay? So I already mentioned this one, right? If you take the cross product of two vectors, that cross product is the third vector, correct? It's going to be perpendicular, or also known as orthogonal, to both of your both of the factors in your cross product. All right. So cross products are orthogonal to the factors, the elements in the cross product. Now, the second formula can also be useful to us, okay? Because it's very similar to the formula for finding the cosine of the angle between two vectors, right? So we just did this a moment ago, right? To find the cosine of the angle between two vectors, you take the dot product, right? And you divide it by you take the dot product and you divide it by the product of the magnitudes, correct? Well, you can also find, using a similar formula, the sine of the angle between two vectors, except you replace the dot product with cross product, okay? Now, notice, however, when I say you replace the dot product with cross product, it's not exactly replacing the dot product with the cross product. You cannot leave this, you cannot leave that magnitude off in the numerator, right? We're not just replacing the dot product with the cross product, because when you take the cross product of two vectors, what sort of creature do you get? Yeah, you get another vector. So notice what you have here on the right-hand side of this formula is a vector. Well, of course, the sine of an angle is not a vector, right? It's a number. You've got to get a number. So that's why you need magnitude here. It's the magnitude of the cross product divided by the product of the two magnitudes. That gives you the sine of the angle between two vectors. And finally now, here's how you can test to see if two vectors are parallel to each other, okay? Because if you take the cross product of two vectors and you get 0, then that means the two vectors are parallel. That's why if you take a cross product of a vector with itself, you get 0, right? Because any vector is parallel to itself. But this is true in general. If you take the cross product of two parallel vectors, you will get 0. So if you take the cross product of two vectors and you don't get 0, that means you have a third vector, right? Well, that third vector is perpendicular to the two factors in the cross product. But if you take the cross product of two vectors and you get 0, that means that the two vectors were parallel to each other to start with. Okay, the third formula is really nice, but it really is a geometry formula. All right, I'm not sure how much we're going to use this, but it's kind of a geometric curiosity. So this says, oh, if you take the cross product of two vectors, that gives you the area of the parallelogram that has the two vectors as adjacent sides. Let me show you a picture of what that is. So this is actually a nice formula for geometry, but you never really learned it in geometry because you don't know about vectors usually at that point, right? So suppose you have just a couple of vectors, right? U and V, just two innocent vectors. And let's assume they're not parallel, okay? So you have these two vectors, and I'm going to draw them so that they have the same initial point. Well, when you draw these two vectors, of course, you can think of them as being the sides of a parallelogram, okay? So you see I drew these two vectors, and then I extended them into a parallelogram. It turns out that the cross product of the two vectors will be the area of that parallelogram. It's kind of sometimes ugly to compute area of parallelograms, is it? In geometry? Yeah, no, a parallelogram is not just yeah, it's not quite that simple, right? Okay, so but there's a formula from geometry for computing the area of a parallelogram. But this simplifies it, okay, nicely. So it's just the cross product of these two vectors. So the two adjacent sides of a parallelogram, if you think of those as vectors, you take their cross product, you'll get the area of the parallelogram. Okay, so we're going to try another cross product here, but this one we're actually even going to try to draw. So that's why I gave you the that's why I gave you the graphing paper. All right, so this one is it's fun to draw, but it's really difficult to draw it so that you see it, so you can see the illustration nicely. Okay, but we're going to give it a shot here. All right, so suppose we have these two vectors. So I minus 4j plus k, and then the second vector 2i plus 3j. Notice that the third component is missing, right? So that's 0. So this is plus 0k. All right. And so the first part of the problem is actually easy. It just says find a vector w that's orthogonal to both of these vectors. So find a vector w that's orthogonal to both of these vectors. Well, you know how to do that, right? Now, right? What do? You just what? Not the dot product, yeah. The cross product, right? Okay. Yeah, the dot product will be a number, all right, and it's a useful number, but the cross product is the vector that's perpendicular. But what I want to do is draw a picture of the situation. So I want to see. I want to try on that 3D graphing paper that I gave you. Try to plot U, try to plot V, and then try to plot the cross product when you find it, and see what it looks like. See if you can make it look like two vectors and then a third vector that is perpendicular to both of them. Notice when you get a third vector that's perpendicular to both of them, you're in three-dimensional space. Okay, right? So if you've got two vectors and a third vector that's perpendicular to both of them, you are drawing a picture in 3 dimensions. Let me see if I can. Oh, there it is. Okay, there's there is the picture. All right, but I'm gonna let you try to plot this one. All right, you see, plot these two, then try to plot them. See if you can find your cross product and see if you can plot that. So let me cover that up because I want y'all to try that. Okay. But you are definitely in 3 dimensions, and you know it's hard to get a hard to give your best shot, but find the cross product first. Okay, at least see if you can do that. This is a math class, right? Not an art class, so you don't have to make your art excellent. But cross product. So if you're having trouble doing the calculations, ask me here. So. So, same. Probably. Careful, that's mine, so. So, now look carefully, watermarked is the X and the Y axes, right? Yeah. See it. See it. See it. Pause. So, nice. Oh, I can change this is the signs right. Oh, from the last one. Oh, darn it. Oh, okay. All right, that's good. You probably did the right thing. I had one already. All right. Right there. think. It's like all right. Thank you. Putting it in. Hey, so are you scared? Are you scared of flying? Oh, we did it on the top. So, almost not. Right. So, all right. Yeah. Okay. This two. I look. Yeah, that's right. So, okay. Oh, y'all are doing really excellent. All right. Let's stop there then. So, I think uh everybody got the cross product right, probably, and the pictures were actually really good. So I think they're the cross product, right? U cross V. If we do this really quickly, okay. So make sure I don't make any arithmetic mistakes there. So there's my table. It really does help to set up the table, all right, to do the cross product. So that will really save you mistakes, all right. So let's see. So again, ignore the first column, right, and then do this cross product. So you'd have minus 4 times 0, right, is 0, and then minus 3 times 1. So you get minus 3 times I, right? Let me fill in a little bit more there. So minus 4 times 0 is 0, right? And then minus 1 times 3 is 3. So you get 0 minus 3 times I, and then minus what's going to be the j coefficient there. So again, ignore the middle column now, and and take this cross product. So 1 times 0 is 0, and then minus 2 times 1, which would be a -2, right? But don't forget, you're changing the sign, right, of that one. And then for the third coefficient, ignore the third column, right? And then take this cross product. So 1 times 3 is 3. And then minus 2 times a -4. So that's -8, but minus a -8 is +8, right? Times k. So you end up with minus 3i plus 2j plus 11 k. That's the cross product there. Did y'all get that right? I think most people got that right. So if you got that much, that's good. The picture there is just kind of gravy. So here's the picture that the book drew of this example. And I think most people got something looking like this. Okay. Actually better than this one, because the first vector goes into which quadrant is this? I'm going to get mixed up on quadrants, right? Is that the fourth quadrant? Yeah, the first vector actually goes slightly into the fourth quadrant, and it's a little bit elevated, right? But not much. The second vector actually lies in the xy plane, right? Because its third coefficient is 0. So the second vector is actually flat there in the xy plane. And then here is your cross product, right? That's supposed to be perpendicular to both of these, vectors. Now, I want to point out, just for future reference, whenever you're given two vectors that are not parallel to each other, right? Whenever you have two vectors that are not parallel to each other, they define a plane in three-dimensional space, okay? So these two vectors, you can think of them as creating a plane in three-dimensional space. A plane now is a flat surface, right? And so there's only one plane, one flat surface that contains these two vectors u and v. It's not the xy plane, okay, right? It's a slightly tilted plane that contains these two vectors u and v. And notice that this cross product vector now is going to be perpendicular to that plane. The plane, P-L-A-N-E, that contains these two vectors, all right? That's going to be a very important observation to us in the future. This isn't a great picture to illustrate that, because it's kind of, because u and v, the plane that contains them is almost flat, right? Because u is just barely elevated. But it is elevated a little bit above the xy plane. So the plane that contains these two vectors is a little bit elevated above the xy plane, okay? All right. Now, we mentioned a moment ago, right, that that you can use vectors to find the area of a parallelogram. Here's a parallelogram drawn in, here's a parallelogram, at least I think it's supposed to be a parallelogram, drawn in three-dimensional space, okay? And maybe we saw this parallelogram before. The corners of that parallelogram are these 4 points in three-dimensional space. And so we want to compute here just quickly the area of this parallelogram, right? Okay. So notice you can extend that parallelogram if you go in all 4 directions, right? You can extend that parallelogram into an infinitely large plane, correct? Right? You could extend that parallelogram into a plane surface that, you know, continues on the left and the right and on the top and the bottom. So we've drawn here just a little piece of that plane that contains those 4 points. All right, so let's see, what was our formula? It's so simple. The area of that parallelogram, right, is a cross product, right? Or the magnitude of a cross product. Yeah, it's a good thing you caught me there, Elijah, because an area is a scalar, that's a number, right? But a cross product is a vector. Okay, so of course an area cannot be the same as a cross product because those are two different creatures. But if you take the magnitude of the cross product, we'll get, of course, a number. All right, now, but let's see what vectors here do we want to compute the cross product of? Well, we need to find the edges, right? Intersecting edges of this parallelogram. So I guess we could use what? The vector here that runs from A to D, right? As one of the edges of the parallelogram. And then also the vector that runs from A to B, right? Take their cross product and then compute the magnitude of that, and that will give you the area of that. That will give you the area of that parallelogram. Now, don't let's fill in then what we're looking here. So we want the vector from A to D, correct? And then take the cross product of that vector with the vector from A to B, right? And then find the magnitude of that cross product. That gives you the area of that parallelogram, right? So it's a simple formula, but it does take a little bit of work to execute. What if you computed this magnitude? So you made a little mistake here, and you tried to compute the cross product of A and D and B and C. What would happen there? That would be 0, right? Why do we know that? Yeah, because these two vectors are parallel, correct? Right? Okay. So when you take the cross product of two parallel vectors, remember you get the 0 vector. And the magnitude of the 0 vector is 0. So this would turn out to be 0. So that's obviously bogus, right? Because we can see that that parallelogram does have an area, right? Okay. Instead, we want this this magnitude. Let's see if we can do that. So what is there? This vector from A to D, if we write that in standard form, is that 0i minus 2j plus 6k? Is that right? So the vector from A to D, right? Okay. 5 minus 5 is 0, right? 5 minus 5 is 0. 0 minus 2 is -2. 6 minus 0 is 6. And then the vector from A to B. So what would we get there? Minus 3i, right? Plus 4j, and then plus k. Is that correct? I think so. And now just compute that cross product and then calculate the magnitude there. All right, so let's try the cross product. All right, so let's see. First multiplication there. Forget that first column, right? So you have minus 2 times 1 is -2, and then minus 4 times 6 on -2, minus 24. Wow, that's huge, right? So -2 minus 24 times I. And then let's see, what's our second coefficient going to be? So forget about this column. So 0 times 1, that's 0 minus minus 3 times 6, which is minus 18. So you get 0 plus 18, but then we have to turn around and change the sign again. So we end up with minus 18 times j, right? Then what about for that third coefficient? Forget about this column. So we have 0 times 4 is 0, right? And then minus 3 times 2 is positive 6. So we get 0 minus 6 times k, right? So altogether, wow, I have a big vector here, right? Minus 26i minus 18j, right? Minus 6 times k. Did I do that right? Somebody will look. Okay, think it's right?
The product over here.
Yes. Right, yeah. Okay. Because you're going to take the magnitude, and magnitudes will be positive in any event, right? Okay. So, all right. So finally there, what's this magnitude? Let's see if we can squeeze this in here, if I can get everything on the same page. So this magnitude is going to be what? The square root of the squares of these coefficients, right? So you have minus 26 squared plus a minus 18 squared, and then plus a minus 6 squared, right? And then just compute the square root of all of that. What is 26 squared? Huh? 676, and then 18 squared. Oh my, I should be what? 324. Is that right? 18 squared? 324. Okay, and then well, I do know minus 6 squared is 36, right? So we have the square root of this big sum. What does that add up to? 1036. So whatever the square root of 1036 is. What is that approximately? 30 something? 32.2. All right, so there's our, apparently that's the area of that parallel. Let me show you one more formula, but I'm not going to we're not going to do the calculations, but it might be in the homework. If we do the calculations, it'll take us forever. If you have 3 vectors that do not lie in the same plane, all right. So remember, if you've got 2 vectors, they always identify a plane, correct? So 2 non-parallel vectors always fall in the same plane. But if you have 3 vectors that all of them do not fall in the same plane, then those vectors, you can think of them as forming the edges of a mass, a solid mass like this one. Notice this is similar to a parallelogram, right? But this is a 3-dimensional object. This is called the parallel pipette, all right? So it's the 3-dimensional equivalent of a parallelogram in 2 dimensions. And it turns out that the triple scalar product will give you the volume of that parallel pipette. Okay, so that's just an interesting formula from geometry there, right? So remember, this is the triple scalar product, the cross product of 2 vectors, right? And then the dot product of third vector. You have to take the absolute value of that because that dot product may turn out to be negative. And of course, volume won't be negative. So this is not magnitude. This is absolute value. Remember, this quantity inside of the absolute values is going to be a number because it's the result of a dot product. Okay. I think there's maybe one problem in the homework that requires that formula. So recall this when you're working on your homework, right? Okay. The volume of a parallel pipette is this triple scalar product. I have an example for this, but here's the picture. But I'm not going to go through the calculations in the example. In the example, we wanted to find the volume of that parallel pipette formed by those three vectors. And again, it's that triple scalar product. So the area there would be U dot B cross W. I'll do those calculations and put that in the notes when I post the notes, but I'm not going to go through them here right now in class. It's just a matter of computing a cross product and then doing a dot product. So I think we've had practice with that. Okay. All right, let's break there and take a few minutes. We'll come back at 12:50, and then finally we're going to start talking about equations in 3 dimensions. You know, that's one of our favorite topics in 2 dimensions, right? Okay. If we have an equation in two variables in 2 dimensions, what sort of curve does that generate? So now we want to extend our knowledge of equations in 2 dimensions to equations in 3 dimensions. All right, and we'll be dealing in 3 dimensions with equations that have 3 variables instead of 2 variables. Okay, and what sort of pictures do we get when we graph the solutions to equations with 3 variables in 3 dimensions? Okay, so you know when you graph solutions to equations, 2 variable equations in 2 dimensions, you get curves. So when we're graphing solutions to 3 variable equations in 3 dimensions, what happens, right? Okay. But let's take a break first, and we'll come back at 12:50 and take up that topic. All right, let's resume here, and now we're going to take ourselves back to like beginning algebra, all right, because we need to remind ourselves of how simple things work in 2 dimensions, because we're going to try to translate that into 3 dimensions, but we really have to make sure we understand what's happening in 2 dimensions before we can start working in 3 dimensions, right? So I wrote down here, this is really this easiest sort of equation that you can write down in 3 dimensions, right? Okay. It's got in 2 dimensions. It's got 2 variables in it, all right? X and Y, and the A, B, and C there are coefficients in the equation. So those are really considered constants. X and Y are the variables. So so if we're thinking about graphing the solutions to this equation, right? Of course, that equation has lots of solutions. So, and when you graph the solutions to this equation, you're going to get some sort of curve. So if you're not just going to graph, naively by plotting points and trying to connect them with a curve, which sometimes works and sometimes doesn't, then you would like to know beforehand, right, what sort of picture, what sort of curve you're going to get when you graph an equation like this one. All right, and this is the simplest sort of equation in 2 variables that I could write down, because both of the variables are only here raised to the first power, right? Okay, so you have really that's kind of the easiest sort of equation in 2 variables that you could think about graphing. Now, if we rewrite the equation a little bit, then we can you'll very quickly recall, if you didn't already, right? You'll very quickly recall what sort of curve you're going to get when you try to graph an equation like this one. So what I did was I took this equation and I solved it for the variable y. That's really easy to do because x and y are just raised to the first power here. So it's really easy to rearrange the equation and solve it for y. So there's the equation solved for y, okay? And then when you look at that a little bit more closely, you realize, oh yeah, that's a linear equation. I know how to graph that equation, right? So the solutions to this equation, when you graph them, you come up with a straight line. So why do we know that this is why do we recall immediately that this is a linear equation? Well, notice you have a coefficient x here, which is minus a over b, but that's just a constant, right? And so we really just have here a constant times x plus, and then you have the second constant, right? C over b, but again, c over b is just a constant, right? Okay, so what you're really looking at there is the equation for a line in slope-intercept form, right? Normally, we would call this a coefficient for the x. We would call that as m, right? Okay, and then we know that this second constant here is the y-intercept, right? So this is really just the equation for a line, and when you solve it for y, you can graph the line very easily, right? Because you know what the slope is. It's the coefficient of x, and you know what the y-intercept here is, right? It's just this constant. It's just this constant at the end. Okay, so so the graph here is just when you graph this equation, just get a straight line. Now, however, I want to show you why this graph or why when you have a straight line and you try to write down the equation that corresponds to the line, you get an equation that looks like this. All right, understand what I'm saying here? Okay, if you start with the equation, first, so suppose I give you an equation that looks like this and say make the graph. Well, you can do that easily just by putting it in slope-intercept form, and now you know the slope and you know the y-intercept, so you can draw the graph easily, right? Okay, but I'm asking the question in the opposite direction. Suppose I drew a line for you. Suppose I drew the line first. So suppose you started with the picture first, not the equation. So suppose I showed you the picture first, and I said, what's the equation that matches this line? Okay, so how do you take the picture and convert it to the equation? So when you're trying to write down the equation for a line, why do you always get an equation that looks like this? All right. Okay. I mean, I know if we start with the equation and graph it, we'll get a line. But when we start with the line and try to write down the equation for the line, why do we always get an equation that ends up looking like this or like this? Okay. So why do straight lines give you equations like y equals mx plus b, right? Okay, which is how you probably learned to memorize, right? The slope-intercept form for the equation of a line. Okay, so we're gonna derive that now. So stick with me because this is going to be important in 3 dimensions. So watch carefully what I'm doing in 2 dimensions. You might think, gosh, you're making this way too complicated in 2 dimensions. Yeah, I am making it a little bit complicated in 2 dimensions, but it turns out to be useful in 3 dimensions, what I'm getting ready to do. All right, so suppose we've got a line and we want to write down the equation that corresponds to that line. Okay, now you have to know some things about the line, right, to write down the equation that corresponds to a line, right? Okay, so so you have to think of yourself, what do you need to know in 2 dimensions in the Cartesian coordinate plane? What piece of information define a unique line, right? What pieces of information can I give you so that you could draw the line, right? Well, one thing is if I told you 2 points that were on the line, right? Okay, so if I told you I'm thinking of a line that goes through these 2 points, you could immediately draw the line, correct? Because there's only one line, according to the axioms of geometry. There's only one line that goes through any 2. Okay, so easy, right? Okay, now I could also tell you, however, a little bit more sophisticated way of describing the line. I could tell you a point on the line, and I could also tell you what, not a second point, but what? Slope, right? Yeah. If I told you a point on the line and the slope, you would also be able to draw a picture of the line. Okay, I trust, because you know how slope works. Okay, so so there's 2 other pieces of information I could use that you could draw the picture of the line. So let's concentrate on that, the slope and a point on the line. Okay. All right, so So let's see. Suppose I tell you, all right, so I'm thinking of a line that has particular slope. I'm just going to call the slope M. All right. And it goes through this point. Okay. So it goes through the point X1, Y1. So you know the coordinates of this point. This is not a variable, right? You know the coordinates of this point. So you know the slope and you know a point that the line goes through. So you could draw a picture, right, of the line, I think, pretty easily with those pieces of information. I also want to write down the equation for the line from those two pieces of information. Okay. All right. Now, this is not the way you do it in algebra class, but this is the way we're going to do it here, calculus 3. We're going to use vectors to help this problem. Okay. So what I'm going to do is let's draw a vector that matches the slope. Okay. So I'm going to draw a vector that matches the slope. You were doing that earlier, right, Elijah, in your homework, correct? Because that was helping you find the angle between two lines, correct? Okay. So I told you the slope was M. All right. And I want to draw a vector that matches that slope. Well, the way I would do that, I guess there are other ways of thinking of this, is I would think of the slope as a fraction. So let's write the slope as a fraction. Okay. Of course, you know that fraction geometrically is rise over run, correct? That corresponds to the rise, right, of the line, and the run also of the line. So here's a picture of my slope vector. There's a picture of my slope vector. I drew the slope vector so it begins at the origin. All right. So that's kind of in standard position, right? The slope vector there starts at the origin, right? So you know this amount would be the run, this amount would be the rise, right, of the slope. So if you wrote down the slope vector, as a vector, what would that look like? It would look like this, right? Okay. The run would be the x component, right, and the rise would be the y component. So this vector here kind of represents the slope. Now let's go back to our line, however. Okay. So what do we know geometrically about lines? Well, if you compute the slope between any 2 points on a line, you always get the same value, right? Okay, so that's just an important property of lines. If you compute the slope between any 2 points on the line, you always get the same. You always get the same number. It doesn't matter how far or apart the lines are, or how far apart the points are, or how close together the points are. If they both are on the same line, if you compute the slope between them, you get the same value each time. Okay, that's true because of the similar triangle theorem from geometry. That's what makes that fact true. Okay. Well, all right. So here's my line. All right, and here's the point on the line. Okay, there's the point on the line. Remember, you know the coordinates of this point. I told you the coordinates of the point. I told you the slope, so you know this value. All right, look, any other point on the line, any other variable point on the line, so this point is a variable, okay? The x and y coordinates are variables here, but it's a point that falls on the line, okay? So this xy here can be any other point on the line. It could be way over here, it could be way back here, but it's got to be a point on. So what do you know? When you calculate what? When you calculate the slope between these 2 points, you always get what? The same number, right? It doesn't matter how far, or it doesn't matter how far to the right this point xy is, or how far to the left this point xy is, right? Remember, this point is fixed, right? Because I gave you this. This is the variable point. Now, I'm not actually going to calculate the slope between these 2 points. What I'm going to do, however, is I'm going to construct the vector, because this is calculus 3. Let's construct the vector between these 2 points. Okay, so between my fixed point that I already gave you, right, and this variable point that's supposed to fall on the line. Well, what does that vector look like? Oh, it's so easy here, right? There it is, right? Yeah. How do you compute vectors? You take the difference in the initial coordinates, right? The difference in the terminal coordinates, and that gives you this vector. So here's the vector. Well, it's in the picture, right? That's this vector right here. What do you know about that vector? that vector has to be parallel to what? The slope vector. It has to be parallel to the slope vector, right? That's the key thing, right? That vector has to be parallel to the slope vector. So that's kind of the calculus 3 way of saying, oh, the slope between any 2 points is the same. The slope vector, the vector between these 2 points has to be parallel to the slope vector. Okay. Again, no matter where that point xy is located, this vector is parallel to the slope vector. So if 2 vectors are parallel, what do we know? Well, I know if I take the dot product, I get what? Is it the dot product? Oh, no, cross product, right? If I take the cross product, I get what? 0. Well, I kind of want to stay away from cross products because that's kind of complicated to do, right? Okay. But what else do we know about parallel vectors? They are what? They're scalar multiples of each other. That's the key. All right. So you know that this vector, the vector along the line, has to be a multiple of the slope vector. Okay. This vector along the line has to be a multiple of the slope vector. So see, you know this is true. This equation is true. Now, what's the t? I'm not sure. It's just some multiple, right? Okay. Could be 1, right? But it could be any other number, right? But this vector has to be some scalar multiple of the slope vector. All right, now what does that mean? Well, let's try filling in a little bit of algebra here then. So if these 2 vectors are equal, then that means the first component is equal, right? So you know x minus x1 has to be equal to what? T times the run, correct? And what's y minus y1 going to be? That's going to be t times the rise, right? Now, that means that t in both cases is, there's 2 different ways of computing t, I should say, not in both cases. From this first equation, you get that x minus x1 over the run is equal to t, correct? And from the second equation, you get t is equal to what? Y minus y1 over the rise, is that right? See, I just divided this equation by run on both sides, right? This equation by rise on both sides, and I got this. But look, this t is the same. So what about these 2 things? They're equal, right? Those 2 things are equal. So let's set them equal to each other. So we have x minus x1 over the run is equal to y minus y1 over the rise. Now, I want to rewrite that. I want to rewrite that equation a little bit. Okay. So let's see what I'm going to do here. Let's multiply. I'm going to start here by eliminating this rise. So I'm going to multiply both sides by the rise. Of course, it crosses out here, right? And then I'm going to turn around and multiply both sides by the run. So I'm going to do also both sides by the run. Let me see if I'm doing this right. Well, let's not try to do all that because I get confused. So multiply both sides by the, just multiply both sides by the rise. Okay. So what does that look like? You get rise times x minus x1 over the run is equal to y minus y1. Is that right? You get this equation? I'm moving from right to left here. Now I'm going to divide both sides by x minus x1. So I'm going to divide both sides by this. So when you divide that out of the left-hand side, that goes away. So you just get rise over run. And when you divide it from the other side, well, you get, well, you just get it divided into the other side because it's not going to cancel. So you get something that looks like this. So y minus y1 over x minus x1 is rise over run. But what's rise over run better known as? Slope. That's the slope. So finally, running out of room here, and stick it down here, we get that the slope is y minus y1 over x minus x1. Oh, that's starting to look familiar, right? So isn't that the slope times x minus x1 is equal to y minus y1? That's point slope. Yeah, there it is. That's point slope form. And if you solve that for y, you're going to get slope intercept form. What would the slope intercept form look like? I think it's going to be y is equal to m times x minus m times x1 plus y1. So there's slope times x, and that's a constant because there are no variables there. So that's the y-intercept right there. So there's slope-intercept form. What did we just show? Some people at this point get confused about what we just did because this is so familiar to them. What did we just prove? Well, we just proved if you start with a line, if you start with the picture of a line and you try to write down its equation, this is what you're going to get, okay? You're always going to get an equation that looks like this, or if you prefer, in this form, right? Slope, a point slope form. So what we just showed is, oh, in 2 dimensions, equations for lines look like this. Cool. Now you knew that already, right? Okay, you knew what equations for lines look like in 2 dimensions. All right, but I just wanted to remind you, how do we know that equations for lines in 2 dimensions look like this? All right, because we want to expand things to 3 dimensions. Now, unfortunately, our intuition takes a real hit here, okay? Because the first thing you're going to think is, I'm just going to add in a third variable, because in 3 dimensions, I can have the x variable, the y variable, but also the variable that corresponds to the z-axis, right? The z variable. So I'm going to write down an equation like this. All the variables just raised to the first power. And that's the simplest sort of equation you can write down in 3 dimensions, right? Because all of your variables are just raised to the first power. This is a constant. This doesn't have a variable. It's just a number. So you're thinking, that must be the equation for a line. If I graph that in 3 dimensions, I'm going to get a nice line in 3 dimensions that's going through space. And unfortunately, that's not true, okay? You do get a nice picture, but you don't get a straight line. Actually, let me show you an example of that. So here's a simple equation in 3 variables, x minus y plus z equals 6. I just made up the 6, all right? So there's a variable in 3 dimensions. I'm sorry, there's an equation in 3 variables, right? Okay, there's an equation in 3 variables. All of the variables are just raised to the first power. So you have a very simple equation in 3 dimensions. But when you graph it, you're not going to get a straight line. Let me show you how you know that's true. Try to plot the intercepts on the axes. So how do you get the z-intercept? Where this equation crosses the z-axis. To get the z-intercept, set x and y to 0. Set x and y to 0. So if you set x and y to 0 in this equation, what do you get? Z equals what? 6. So if x and y are 0, z is going to be 6. X and Y being 0 would be, here's the XY plane. So that's the origin, right? So if X and Y are 0, you're right on the origin, go up to 6 on the x-axis. Now, if you look for the x-intercept, that's where y and z are 0. I and z are 0. That is going to also 6, right? So I and z are 0. I and z are 0. Okay, I and z are both 0. Then x is 6. That's on the x-axis. And when likewise, if you set x and z to 0, get y is -6. So the intercept on the y-axis is down here, -6. Those 3 points not fall on the line. They don't fall. So this is not, when you graph this equation, that's back. That means lines in 3 dimensions are more complicated than all. Okay. What you do get when you graph that equation, though, is you do get a nice picture. You get a plane, you get a flat plane, and here's a little piece of that. There's a little piece of that. Right? Now that plane actually extends out. Okay, this is just a little triangle section. That plane, of course, actually extends out to infinity on the left and right and bottom. All right, just one second. So straight lines in 3 dimensions are going to be unfortunately harder. They are in 2 dimensions. That's that. What is easy, however, in 3 dimensions are planes. All right, those turn out to be simple. Let's see. All right, so we have to take up next time. What do the equations for lines in 3 dimensions if you have a line going through space? What is it? Is it not? It's all right. And then, well, what about graphs of plane? Okay. Obviously, straight and based on that example. All right, so we'll take that up next time. Those will be our first 2 types of graphs in 3 dimensions, and we're going to make use of those. Okay, because as you know, lines play an important role in calculus, right? So we're going to make use of these 2 types of 3-dimensional figures in helping us with calculus in 3 dimensions as well. Okay, all right, so we're out of time. Oh, yeah, we're out of time. I ran over. All right, so I will see you guys on Wednesday. All right, finish your homework tonight. Yes, ma'am. No, I was just showing that, right? It's look on the website. It's been postponed till